Galaxies are among the most magnificent structures in the universe. Immense, sprawling collections of stars, dust, gas, and dark matter bound together by gravity, forming the backbone of cosmic architecture. To understand galaxies is to peer into the story of matter itself, the organization of the universe, and even the ingredients that make up our own planet and bodies. When we look into the night sky, the stars we see are only a tiny portion of the Milky Way galaxy, our home. But beyond it lies a vast cosmos filled with trillions of galaxies, each containing billions or even trillions of stars, many of which have their own planetary systems. The word galaxy comes from the Greek Galaxies, meaning milky, a reference to the hazy band of light across the sky that the ancients named the Milky Way. For centuries, humans believed that this glowing trail of stars was the entirety of the universe. It wasn't until the 20th century that astronomers realized the Milky Way was just one among countless others. This revelation completely transformed our understanding of scale in the cosmos. From a geocentric view to a heliocentric one, and ultimately to a cosmocentric perspective, each step pushed us further from the center and deeper into understanding the true nature of the universe. Galaxies come in a surprising variety of shapes and sizes, and astronomers have devised systems to classify them. The most familiar type may be the spiral galaxy, like the Milky Way, characterized by sweeping arms of stars that curl outward from a bright central bulge. These spirals are often sites of intense star formation, where new stars are constantly being born from vast clouds of gas and dust. Other galaxies, known as elliptical galaxies, have a more rounded, oval shape and tend to contain older stars with little new star formation. Then there are irregular galaxies, which, as their name suggests, lack any clear structure and often appear distorted or chaotic, sometimes due to gravitational interactions with other galaxies. Understanding the types of galaxies helps scientists uncover their life histories. Spiral galaxies tend to be younger and more dynamic, while ellipticals are usually older and more evolved, often the result of mergers between smaller galaxies. The irregulars tell stories of disruption and turbulence, caught in the gravitational dance of cosmic collisions. But despite their differences, all galaxies share some essential components: stars, nebulae, gas clouds, and dark matter. Each of these elements contributes to the galaxy's behavior and evolution, influencing everything from how it rotates to how it forms new stars. One of the most fascinating aspects of galaxies is their role as fundamental building blocks of the large-scale structure of the universe. They are not randomly distributed in space, but form vast webs, clusters, filaments, and superclusters that weave through the cosmos like cosmic lace. Between these structures are enormous voids, dark and nearly empty expanses that separate the glowing islands of galaxies. This web-like distribution, known as the cosmic web, suggests that the universe is not only structured but interconnected in ways that reflect its origins and ongoing evolution. The study of galaxies also opens a window into other key phenomena in astrophysics, such as the behavior of dark matter and dark energy. Galaxies rotate in ways that can't be explained by the visible matter alone, suggesting the presence of a hidden mass, dark matter, that exerts gravitational influence but emits no light. This invisible scaffold holds galaxies together and shapes the distribution of matter on a cosmic scale. Moreover, the accelerating expansion of the universe, attributed to dark energy, affects how galaxies move away from one another over time. Another crucial point of interest is the relationship between galaxies and star formation. Galaxies are the nurseries where stars are born, live out their lifespans, and eventually die, often in dramatic fashion as supernovae. These processes release energy and elements that recycle back into the galactic environment, enriching it for the next generation of stars and planets. Over billions of years, this cycle has produced the diversity of chemical elements that make life possible. In a very real sense, galaxies are engines of creation, constantly turning simple gases into the complex ingredients of planets and biology. Yet, galaxies are also places of destruction and transformation. The death of stars, the merging of galaxies, and the presence of supermassive black holes at their centers all contribute to the dynamic and sometimes violent lives of these systems. Black holes, in particular, are found at the heart of nearly every large galaxy and can affect their host galaxies in profound ways. Their intense gravity can strip material from surrounding stars and gas clouds, producing jets of energy that stretch for thousands of light years. These processes not only illuminate galaxies, but also regulate star formation, acting as both creators and destroyers. Galaxies also serve as cosmic time machines. Because light takes time to travel, when we look at distant galaxies, we're seeing them as they were millions or even billions of years ago. The most distant galaxies are among the first that formed after the Big Bang, offering clues about the early universe and the conditions that led to the structure we see today. Telescopes like the James Webb Space Telescope are now reaching farther than ever before, capturing images of galaxies that formed only a few 100 million years after the Big Bang. These discoveries are rewriting what we thought we knew about how galaxies began and how fast they grew. The scientific study of galaxies is deeply rooted in observation, mathematics, and theory, but it also touches on something more abstract: our desire to understand where we come from. Gazing into the heavens has long inspired myths, art, and philosophical reflections. Galaxies are not only physical objects, they are symbols of infinity, mystery, and the vastness of the unknown. They remind us of our small place in the cosmos, but also of our ability to comprehend and explore it. The fact that tiny beings on a pale blue that can ask questions about galaxies billions of light years away is itself a kind of miracle. This is just the beginning. As we follow the formation of galaxies from primordial gas to spiral arms and starbursts, we step into a timeline that spans nearly 14 billion years. Each stage reveals not only a piece of cosmic history, but a part of our own. Galaxies are not just out there. They are the context of everything that exists, including us. To understand how galaxies came to be, we must first journey to the very beginning of time itself, to the moment of the Big Bang, approximately 13.8 billion years ago. In this singular event, space and time burst into existence along with all the energy and matter that would eventually form stars, planets, and galaxies. In the initial fractions of a second, the universe expanded at an incredible rate in a process known as cosmic inflation. This expansion smoothed out any irregularities, but also left tiny quantum fluctuations imprinted on the fabric of space-time, imperfections that would later serve as the seeds of cosmic structure. As the universe continued to expand and cool, it entered the epoch known as the recombination era, around 380,000 years after the Big Bang. During this phase, temperatures dropped enough for electrons and protons to combine into neutral hydrogen atoms. This seemingly simple event had profound consequences. It rendered the universe transparent to radiation for the first time, allowing photons to travel freely. The light released at this moment is what we now detect as the cosmic microwave background, CMB, a faint afterglow that serves as a snapshot of the infant universe. The CMB contains slight temperature variations that map the density fluctuations present at that time. These small fluctuations in the CMB were not random. Under the influence of gravity, the denser regions began to pull in more matter, growing slowly over time. This marked the beginning of a long and intricate process, the collapse of gas into denser clumps under gravity, the initial step toward forming the first galaxies. However, this gravitational pull was not happening in isolation. Dark matter, an invisible but dominant component of the cosmos, was also clumping together. Though we still don't know exactly what dark matter is, its gravitational effects are unmistakable. It formed massive halos that acted as cosmic scaffolding, drawing normal matter toward them. Before the first stars ever lit up the universe, the cosmos experienced a period known as the Dark Ages. During this time, the universe was filled with a diffuse, cold hydrogen fog. There was no light, no stars, and no galaxies, just slowly accumulating clouds of gas and dark matter. For about 200 million years, this silence persisted. But all the while, gravitational forces were working invisibly, gradually intensifying the density of certain regions. Eventually, this led to the formation of stars. The first stars, known as population 3 stars, were unlike anything we observe today. Composed almost entirely of hydrogen and helium, these stars were massive, often hundreds of times the mass of our Sun, and burned incredibly bright and hot. However, they had short lifespans, often lasting only a few million years. Their violent deaths in supernova explosions seeded the universe with heavier elements like carbon, oxygen, and iron, paving the way for more complex chemistry and, eventually, life. These first stars also emitted vast amounts of ultraviolet radiation, which began to reionize the surrounding hydrogen, turning the fog of the Dark Ages transparent once more. This phase transition, known as the Epoch of Reionization, marked the emergence of the first light in the universe since the CMB and dramatically altered the intergalactic medium. Meanwhile, the regions of space where these stars were forming also contained dense gas clouds and dark matter. Over time, these areas began to coalesce into the first protogalaxies. These early galactic structures were small by modern standards, perhaps only 1,000th the mass of the Milky Way, but they represented the first step toward the majestic galaxies we see today. The growth of these structures was accelerated by a series of mergers and accretions. Smaller protogalaxies collided and combined to form larger systems. These collisions were chaotic and sometimes destructive, but they also stimulated the birth of new stars, reshaping the galaxies in the process. Over billions of years, this cycle of merging and star formation continued, creating ever larger and more complex galactic systems. So, the early universe was not a static place. It was dynamic, filled with feedback loops of matter and energy, gravity, and radiation. The transformation from a uniform soup of particles to a universe rich in structure and variety was both slow and violent. But at each stage, the interplay of physics and chance molded the cosmos into its current form. In this way, galaxies were not born in an instant, but emerged gradually through a combination of quantum fluctuations, gravitational collapse, star formation, and cosmic chemistry. Each galaxy is a product of billions of years of evolution, and each carries with it a record of the universe's earliest history. Galaxies are among the most magnificent and complex structures in the universe. They are vast systems made up of billions to trillions of stars, enormous clouds of gas and dust, dark matter, and sometimes even supermassive black holes at their cores. Galaxies can be spiral, elliptical, or irregular in shape, each with distinct properties and evolutionary histories. Understanding galaxies is crucial not only because they house the stars and planetary systems, including our own solar system, but also because they serve as the building blocks of the universe's large-scale structure. After the Big Bang, about 13.8 billion years ago, the universe was a hot, dense soup of particles. As it expanded and cooled, protons and neutrons combined to form simple atomic nuclei, primarily hydrogen and helium. This primordial gas filled the early universe. However, this gas was not perfectly uniform. Tiny quantum fluctuations left imprints in the cosmic microwave background, a faint glow that still fills the sky. These fluctuations represented slight over- and underdensities in matter, which would eventually lead to the formation of galaxies. Dark matter, an invisible and mysterious form of matter that does not emit or absorb light, played a key role in the early universe. Its gravitational pull helped amplify the tiny fluctuations in density, leading to the formation of dark matter halos. These halos acted as gravitational wells, attracting and collecting the surrounding gas. As the gas cooled, it began to collapse into these halos, forming rotating clouds. Over time, these rotating protogalaxies became more structured, setting the stage for the birth of stars. The first stars, known as population 3 stars, were formed within these protogalactic clouds. They were composed almost entirely of hydrogen and helium, as heavier elements had not yet been created. These stars were massive and short-lived, burning through their fuel quickly and ending their lives in dramatic supernova explosions. These explosions scattered the first heavy elements, like carbon, oxygen, and iron, into the surrounding space, enriching the interstellar medium and enabling the formation of later generations of stars and planets. As these early stars exploded and seeded their environments with metals, feedback processes such as radiation and stellar winds began to shape their host galaxies. Protogalaxies grew through a combination of star formation and the accretion of gas. However, perhaps the most transformative events in galactic history were mergers. Small galaxies frequently collided and merged, forming larger and more complex systems. These interactions triggered bursts of star formation, reshaped galactic structures, and helped create the variety of galaxy types we observe today. Galaxies do not evolve in isolation. Over time, they began to cluster together under the influence of gravity, forming groups, clusters, and eventually superclusters. These massive structures are interconnected by filaments of dark matter and gas, outlining the cosmic web. Even our own Milky Way is a product of such cosmic evolution. It has absorbed numerous smaller galaxies in the past and continues to do so, including its ongoing interaction with the Magellanic Clouds and its eventual merger with the Andromeda Galaxy in about 4.5 billion years. The diversity in galaxy shapes, spiral, elliptical, and irregular, can largely be attributed to their evolutionary paths. Spiral galaxies like the Milky Way have prominent disks and spiral arms filled with young stars and active star formation. Elliptical galaxies, on the other hand, tend to be older, with little gas and a more spherical or ellipsoidal shape. Irregular galaxies defy simple classification and often result from gravitational interactions or collisions. Angular momentum, star formation rates, and environmental factors all play roles in determining a galaxy's morphology. At the center of nearly every massive galaxy lies a supermassive black hole, millions to billions of times the mass of the Sun. These black holes have a profound influence on their host galaxies. During periods of active accretion, they can become quasars or active galactic nuclei, emitting vast amounts of energy that can regulate star formation by heating and expelling gas. Interestingly, there appears to be a correlation between the mass of a galaxy's central black hole and the properties of its bulge, suggesting a coevolutionary relationship. Galaxies are also held together and influenced by dark matter. One of the key pieces of evidence for dark matter comes from galactic rotation curves, which show that stars far from the center of galaxies orbit much faster than expected based on visible mass alone. This suggests the presence of an unseen mass, dark matter, forming extended halos around galaxies. These halos provide the scaffolding that holds galaxies together and plays a critical role in their formation and stability. Yet, despite its importance, the true nature of dark matter remains one of the biggest mysteries in cosmology. More than just collections of stars, galaxies are dynamic ecosystems. Within them, stars are born from dense clouds of gas, live out their lives, and eventually die, often returning material to the interstellar medium through supernovae or stellar winds. This recycled material can then form new stars, continuing the cycle. In addition to star formation, galaxies exhibit complex interactions involving radiation, magnetic fields, and galactic winds, all of which shape their evolution. The life cycles of stars contribute to broader galactic cycles. Stars form in nebulae, the vast clouds of gas and dust that serve as stellar nurseries. Depending on their mass, stars end their lives as white dwarfs, neutron stars, or black holes. These processes return elements to the galaxy, enriching future generations of stars and even forming the basis of planets and life. It's a poetic truth that humans are literally made of stardust, as many of the atoms in our bodies were forged in ancient stars. Our home galaxy, the Milky Way, has its own unique history. It features a central bulge, a disk with spiral arms, a halo of stars and dark matter, and numerous satellite galaxies. The Sun, along with the entire solar system, orbits the center of the Milky Way at an astonishing speed of about 828,000 kilometers per hour, completing one orbit roughly every 225 to 250 million years. Looking ahead, the Milky Way is on a collision course with the Andromeda Galaxy, a monumental event that will reshape both galaxies into a new elliptical or lenticular form. Beyond science, galaxies have captured the human imagination across cultures and eras. Ancient civilizations often associated the Milky Way with divine or mythical symbols. In modern times, galaxies feature prominently in science fiction, representing distant realms of possibility. The spiral shape itself appears in nature, from hurricanes to fingerprints to DNA, serving as a universal motif. Artists, philosophers, and scientists alike have used galaxies as metaphors for consciousness, order, and the infinite. In recent years, the idea of a multiverse has gained traction in theoretical physics. If other universes exist, they might also host galaxies, though potentially governed by entirely different physical laws. Speculations range from antimatter galaxies and mirror universes to living galaxies that possess some form of consciousness. These ideas stretch the boundaries of science and imagination, inviting us to consider possibilities far beyond our own observable cosmos. Despite our advancements, many questions remain. Why do galaxies spin so quickly? What determines where and when galaxies form? Could they have life cycles, growing and dying like organisms? And what exists in the immense voids between clusters? The study of galaxies not only illuminates the history of the universe, but also challenges us to keep seeking answers to the deepest cosmic mysteries. The emergence of the first stars marked a dramatic transformation in the universe. Until this point, the cosmos had been dominated by gas and dark matter, with no sources of light beyond the fading glow of the cosmic microwave background. But within the dense clumps of hydrogen and helium formed during the cosmic dark ages, gravity continued to pull material inward. As these clouds contracted under their own weight, they heated up. Eventually, in some regions, the conditions became extreme enough to trigger nuclear fusion, the process that powers stars. With this ignition, the universe experienced its first true illumination, a phenomenon known as cosmic dawn. The very first stars, known as population 3 stars, were unlike any that exist today. They formed in an environment composed almost entirely of hydrogen and helium, with virtually no heavier elements, what astronomers call metals. Because metals are crucial in cooling gas clouds and regulating star formation, the lack of them meant these primordial stars grew to be extremely massive, often exceeding 100 times the mass of our Sun. Their enormous mass gave them short, intense lifespans. They burned brightly and died quickly, often within a few million years, a blink of an eye in cosmic terms. These early stars played several essential roles in shaping the evolving universe. First, their light began the process of reionization. During the cosmic dark ages, most hydrogen existed in a neutral state, which was opaque to ultraviolet light. The powerful radiation from population 3 stars ionized this hydrogen, stripping electrons from atoms and transforming the intergalactic medium into a transparent plasma once again. This process, called reionization, took hundreds of millions of years and fundamentally altered the physical conditions of the universe, allowing light to travel more freely. Second, the deaths of these stars and supernova explosions had an enormous impact on their surroundings. When a massive star reaches the end of its life, its core collapses, and the outer layers are ejected in a violent detonation. These supernovae not only released tremendous energy, but they also produced and dispersed heavier elements, carbon, oxygen, nitrogen, iron, into space. These elements seeded the universe with the raw materials necessary for forming more complex stars, planets, and eventually life. Every atom in our bodies heavier than hydrogen was forged in such a stellar furnace. As population 3 stars died out, new generations of stars began to form from enriched material. These later stars, known as population 2, contained small amounts of metals, which made them cooler and more stable than their predecessors. They often formed in clusters within growing clouds of gas, creating the first true stellar systems. These clusters coalesced into what we now call protogalaxies, early versions of galaxies, still chaotic and poorly structured, but already exhibiting many characteristics of modern systems. Protogalaxies emerged in the densest regions of dark matter halos. As gas continued to fall into these gravitational wells, it rotated and formed disks, often with central bulges and active star formation. These structures were far smaller and more irregular than galaxies today, but over time, repeated cycles of star formation and feedback from supernovae helped shape and stabilize them. High-energy radiation and stellar winds from young stars pushed back against the infalling gas, regulating the pace of star birth and preventing premature collapse. During this period, galactic structures began to diversify. Some protogalaxies started to form spiral arms due to rotational dynamics and the distribution of angular momentum. Others remained clumpy and irregular, shaped by gravitational interactions and turbulence. Many of these early galactic forms would later collide and merge, further accelerating their evolution into larger, more organized systems. In addition to stars, other structures began to emerge within these young galaxies. Black holes, formed from the remnants of the most massive stars, started to accumulate mass by drawing in nearby gas and dust. Over time, some of these black holes grew into supermassive black holes, anchoring the centers of galaxies and exerting powerful influences on their growth. Jets and radiation from matter falling into these black holes helped heat the surrounding gas and regulate the rate of star formation. The universe during this epoch was incredibly active and dynamic. The formation of stars and protogalaxies was not a gentle process, but rather a tumultuous era marked by explosive events, intense radiation, and constant transformation. Every feedback loop, whether from supernovae, stellar winds, or black hole activity, played a role in determining which structures survived and grew and which dispersed or collapsed. One of the most fascinating consequences of early star and galaxy formation is the emergence of structure on multiple scales. As protogalaxies merged and accreted mass, they formed larger and more complex systems. Some became elliptical galaxies, dominated by older stars and shaped by past collisions. Others retained enough gas to keep forming new stars, evolving into spiral galaxies. Meanwhile, groups of galaxies began to cluster together under mutual gravitational attraction, forming the precursors of galaxy clusters and superclusters. The process that began with tiny quantum fluctuations in the early universe had now produced the first visible structures, points of light that would eventually form the luminous web of the cosmos. Each of these fledgling galaxies contained hundreds of thousands to millions of stars, bound together by gravity and embedded in a scaffold of dark matter. Though the universe was still young, it had already laid the foundation for the rich cosmic diversity we see today. Modern telescopes, such as the James Webb Space Telescope, now allow astronomers to peer back into this ancient era. By capturing the faint infrared glow of galaxies formed more than 13 billion years ago, scientists can observe the universe as it appeared shortly after these first stars ignited. These observations confirm many aspects of our theoretical models, but also raise new questions. For instance, some galaxies appear larger and more mature than expected at such early times, suggesting that our understanding of star formation and galactic evolution may still be incomplete. The era of first light was a turning point in cosmic history. It ended the long darkness that followed the Big Bang and began the process of structure formation that would eventually lead to planets, ecosystems, and observers like ourselves. In each star that flickered into life, in each explosion that enriched space with elements, the universe wrote another line in its unfolding story, a story still being read and reinterpreted with every new discovery. As the universe aged, the gravitational interactions between galaxies began to shape their destinies in more dramatic and complex ways. In the young cosmos, galaxies were more closely packed together than they are today, and the gravitational pull between them was stronger due to their relative proximity. This environment led to frequent encounters, collisions, and mergers, cosmic events that would become crucial drivers of galactic evolution. Mergers between galaxies are among the most powerful transformative events in the universe. Unlike collisions between solid objects, galaxy mergers do not typically involve stars crashing into one another. This is because, despite the enormous number of stars within galaxies, the vast distances between individual stars make direct collisions exceedingly rare. Instead, the gravitational fields of the interacting galaxies disrupt the orbits of stars, redistribute gas and dust, and often trigger massive waves of star formation known as starbursts. When two galaxies begin to interact, their mutual gravitational attraction causes them to distort. Tidal forces stretch out long streams of stars and gas, forming tidal tails and bridges between the galaxies. These features can be spectacularly beautiful, tracing the invisible threads of gravitational energy binding the galaxies together. Over time, the galaxies spiral inward toward each other, eventually coalescing into a single, larger system. During this process, gas clouds are compressed, leading to a frenzy of star formation as the raw material for new stars is suddenly made dense enough to ignite. One of the most important results of galactic mergers is the change in morphology. Two spiral galaxies merging will often result in the formation of an elliptical galaxy. The original spiral structure is disrupted by the chaotic motion introduced by the collision, and the stars settle into more randomized orbits, creating a rounder, more spheroidal shape. This explains why elliptical galaxies are more common in galaxy clusters, where collisions are more frequent due to higher galactic densities. Not all mergers are between equals. Often, a larger galaxy will collide with and absorb a smaller one in a process known as galactic cannibalism. This phenomenon is common throughout the universe and has played a major role in the growth of many large galaxies, including our own Milky Way. Evidence of past mergers can be found in streams of stars that arc through galactic halos, remnants of smaller galaxies torn apart and assimilated over billions of years. Indeed, the Milky Way has had a tumultuous past. Astronomers have identified several dwarf galaxies currently being consumed by the Milky Way, such as the Sagittarius dwarf spheroidal galaxy. In addition, the Milky Way has stellar streams, trails of stars left behind by smaller galaxies that have been stretched and absorbed. This ongoing process is not just historical. It is a continuing part of our galaxy's evolution. The future of our galaxy also includes a major merger event. In approximately 4.5 billion years, the Milky Way is predicted to collide with the nearby Andromeda Galaxy. This cosmic encounter will not be a destructive crash, but rather a slow dance of gravitational interaction over several billion years. The result will likely be the formation of a new, larger elliptical galaxy, sometimes dubbed Milkomeda. During this event, it is possible that some stars will be flung into intergalactic space, while others will settle into new, more stable orbits within the merged system. Galaxy mergers also play a vital role in the growth of supermassive black holes. Most, if not all, large galaxies harbor a supermassive black hole at their center. When galaxies merge, their central black holes spiral inward toward one another, eventually merging as well. This process can release tremendous gravitational waves, ripples in the fabric of space-time that scientists are just beginning to detect with instruments like LIGO and Virgo. The merging of black holes also helps to regulate star formation, as the energetic feedback from their accretion disks can heat surrounding gas, preventing it from collapsing into new stars. Beyond mergers, galaxies evolve in other ways. Gas inflows from the intergalactic medium can sustain star formation long after a galaxy's original supply of gas has been depleted. Feedback mechanisms, such as stellar winds, radiation from young stars, and jets from black holes, regulate this gas supply, maintaining a balance between collapse and dispersal. The rates of these processes determine whether a galaxy remains active, forming new stars, or becomes quenched, with little ongoing star formation. Environmental factors also influence galaxy evolution. Galaxies in dense clusters are subject to additional forces, such as ram pressure stripping, where the hot gas in the cluster's intergalactic medium removes gas from a galaxy moving through it. This process can quench star formation and transform spiral galaxies into ellipticals. Additionally, gravitational interactions within clusters can induce further mergers or disrupt a galaxy's structure without a full collision, phenomena known as harassment or tidal stripping. Over billions of years, these processes sculpt galaxies into the diverse forms we observe today. Some remain elegant spirals with bright arms and active star nurseries. Others become featureless ellipticals filled with older stars and little remaining gas. Irregular galaxies, often shaped by repeated interactions and mergers, stand as records of chaotic histories. Each galaxy is a dynamic, evolving system with its own unique trajectory shaped by its mass, environment, and interactions. On the largest scales, galaxies are not isolated entities, but part of vast structures. Galaxy groups, clusters, and superclusters. These arrangements form an immense cosmic web, with filaments of dark matter and gas linking thousands of galaxies across millions of light years. The formation of these large-scale structures is influenced by the same gravitational processes that guide mergers and evolution on smaller scales. The same principles of attraction, collision, and feedback play out across the full range of cosmic sizes. As we observe galaxies at various distances, and thus at various stages in the universe's history, we see the continuous unfolding of these evolutionary processes. Distant galaxies appear smaller, more irregular, and more active, reflecting the turbulent conditions of the early universe. Nearby galaxies, older and more stable, showcase the long-term outcomes of countless interactions and internal transformations. This cosmic archaeology allows astronomers to piece together the story of galactic evolution as though reading pages from different chapters of the universe's timeline. Galaxy mergers and evolution are not just phenomena of destruction and chaos. They are engines of creativity and transformation. Through them, matter is redistributed, stars are born, black holes grow, and new structures emerge. These processes reveal the dynamic and interconnected nature of the universe, where nothing is static and every galaxy is a witness to the ever-changing cosmos. The diverse shapes of galaxies across the universe present both a visual wonder and a scientific puzzle. Why do some galaxies appear as graceful spirals while others take the form of smooth, featureless ellipses or irregular, chaotic assemblies? The field of galactic morphology, the study of galaxy shapes and structures, offers crucial insights into the physical processes that shape galaxies over billions of years. These differences in morphology are not merely aesthetic. They are the direct result of the history, environment, and internal dynamics of each galaxy. The two most common types of galaxies are spiral and elliptical. Spiral galaxies, like the Milky Way, are characterized by their flat, rotating disks, prominent spiral arms, and central bulges. The spiral arms are sites of active star formation, glowing with the blue light of young, massive stars. These structures are not fixed, but dynamic patterns of density waves, regions of higher pressure that compress gas and trigger the birth of new stars. The spiral form is a delicate balance of angular momentum, gravity, and ongoing infall of interstellar gas, which fuels continued star formation. Elliptical galaxies, in contrast, lack the ordered structure of spirals. They range from nearly spherical to elongated ellipsoids and have little to no disk-like rotation. These galaxies are typically populated by older, redder stars and have much less interstellar gas and dust. Star formation in elliptical galaxies has largely ceased, and their stars follow randomized orbits, giving the galaxies a smooth, featureless appearance. Ellipticals are most often found in dense environments such as galaxy clusters, suggesting that their morphology is strongly influenced by frequent interactions and mergers. Irregular galaxies do not conform to the neat categories of spiral or elliptical. They often appear chaotic, without any clear structure or symmetry. Many irregular galaxies have been distorted by past gravitational interactions or collisions, which disrupted their original shapes. Others may be small systems that never had enough mass or angular momentum to form a coherent structure. Despite their disordered appearance, irregular galaxies are often rich in gas and active in star formation, playing a vital role in galactic evolution. What determines whether a galaxy becomes spiral, elliptical, or irregular? A major factor is angular momentum. Galaxies that form in environments where the initial gas clouds have significant spin tend to form disks, which can evolve into spiral galaxies. Angular momentum stabilizes the gas against rapid collapse and allows for the formation of orderly structures like spiral arms. On the other hand, If a galaxy undergoes major mergers, especially with another galaxy of similar mass, the ordered motion is disrupted, and the result is often an elliptical galaxy. Mergers are therefore a central mechanism in morphological transformation. A spiral galaxy that collides with another may lose its disk structure. Its gas may be compressed into a central starburst, and the resultant randomization of stellar orbits may yield an elliptical galaxy. The frequency and scale of such interactions are influenced by a galaxy's location. In dense regions like galaxy clusters, mergers and interactions are more common, and elliptical galaxies dominate. In more isolated environments, spiral galaxies are more likely to survive and maintain their structure. Barred spiral galaxies are a fascinating subclass of spirals that contain a central bar-shaped structure made of stars. This bar often acts as a dynamical engine, channeling gas from the outer regions of the galaxy toward the core, where it can fuel star formation or feed a central black hole. Bars are thought to be a natural result of instabilities in the rotating disk and are found in a significant fraction of spiral galaxies, including the Milky Way. Another intriguing type is the ring galaxy. These systems feature a prominent ring of stars and gas, often surrounding a less populated central region. Ring galaxies are usually formed through collisions, when a smaller galaxy passes directly through the disk of a larger spiral galaxy, creating density waves that propagate outward like ripples in a pond. These waves compress gas and trigger star formation, resulting in the bright, ring-like appearance. Lenticular galaxies, which bridge the gap between spirals and ellipticals, possess a disk-like spiral galaxies but lack prominent arms and significant star formation. These galaxies are thought to have evolved from spirals that exhausted or lost their interstellar gas, perhaps through interactions or internal feedback processes. Lenticulars are common in cluster environments and may represent a transitional morphology influenced by external conditions. Beyond individual galaxies, morphology is also connected to cosmic time. In the early universe, galaxies were smaller, more irregular, and more actively forming stars. Over time, mergers and accretion events led to the buildup of larger, more structured systems. By studying galaxies at different distances, therefore at different stages of cosmic history, astronomers can trace the evolution of morphological types over billions of years. Observations with the Hubble Space Telescope and other instruments have revealed a dynamic universe in which galaxy shapes are constantly changing. Simulations have become powerful tools in understanding galaxy morphology. Cosmological simulations can model the formation of galaxies from the Big Bang to the present, incorporating gravity, gas dynamics, star formation, and feedback processes. These simulations reproduce many of the observed features of real galaxies, confirming that morphology is shaped by a complex interplay of initial conditions, dark matter halos, cosmic environment, and evolutionary history. Morphology is also linked to galactic habitability, the potential for planets and life to exist within galaxies. Spiral galaxies, with their ongoing star formation and rich chemical diversity, are more likely to host planetary systems like our own. Elliptical galaxies, by contrast, may have fewer opportunities for life, as they lack the fresh gas needed to form new stars and planets. The structure and dynamics of a galaxy influence everything from the frequency of supernovae to the stability of planetary orbits, making morphology a key factor in the cosmic context of life. Finally, the study of morphology offers a bridge between science and aesthetics. The shapes of galaxies evoke a sense of wonder, symmetry, and complexity that has inspired artists, philosophers, and scientists alike. Spirals recur not just in galaxies, but in natural systems across scales, from hurricanes to seashells to DNA. This universal pattern speaks to deep principles of structure and flow, linking the cosmos to the biological and even the spiritual. In conclusion, galaxy morphology is far more than a classification system. It is a window into the life history of galaxies, revealing how they form, evolve, and interact with their environment. Whether spiral, elliptical, or irregular, each shape tells a story written in the language of gravity, gas, stars, and time. Understanding these shapes allows us to read the narrative of the universe itself. At the heart of nearly every large galaxy lies one of the most mysterious and powerful entities in the cosmos, a supermassive black hole. These titanic objects, often millions or even billions of times the mass of our Sun, reside at galactic centers and exert a profound influence on the behavior and evolution of their host galaxies. The relationship between supermassive black holes and galaxies is not merely coincidental. Evidence suggests they grow together, shaping one another over cosmic time through a process that is still not entirely understood. Black holes themselves are regions of space-time where gravity is so intense that nothing, not even light, can escape. While stellar mass black holes form from the collapse of massive stars, supermassive black holes require a different formation mechanism. Their origins remain one of the great unsolved problems in astrophysics. Some theories propose that they grew from the direct collapse of massive gas clouds in the early universe, bypassing the star phase entirely. Others suggest that smaller black holes merged over time to form larger ones, aided by dense stellar environments and abundant gas. Observational evidence for supermassive black holes comes from the motion of stars and gas near galactic centers. In the Milky Way, for example, astronomers have tracked individual stars orbiting an invisible object at tremendous speeds near the center of the galaxy. These stellar orbits reveal the presence of an extremely massive, compact object known as Sagittarius A*, our galaxy's central black hole. Despite its immense mass, around 4 million solar masses, it fits within a space no larger than our solar system. The discovery of similar central black holes in other galaxies, especially in elliptical and spiral galaxies with prominent bulges, has led to a remarkable realization. The mass of the central black hole is closely related to the mass of the galaxy's bulge. This correlation, known as the M-sigma relation, implies a coevolutionary link. Somehow, galaxies and their black holes know about each other, growing in tandem through a feedback process that connects the smallest and largest scales. One of the most dramatic manifestations of supermassive black holes is the phenomenon of active galactic nuclei, AGN. When large amounts of gas fall into a black hole, they don't disappear quietly. Instead, the gas forms a hot, swirling accretion disk, heated to extreme temperatures by friction and gravitational forces. This disk emits enormous amounts of energy across the electromagnetic spectrum, from radio waves to X-rays. In some cases, jets of relativistic particles shoot out from the galaxy's center at near-light speed, extending for thousands or even millions of light years. These luminous objects, known as quasars when observed at great distances, are among the brightest objects in the universe. During their peak activity, quasars can outshine the entire host galaxy, despite occupying a region no larger than our solar system. Most galaxies, including the Milky Way, likely went through an active phase in their youth. Today, many of these central black holes are relatively quiet, having used up or expelled most of the gas that once fed them. The energy output from AGN has far-reaching consequences. It can heat or expel gas from the galaxy, shutting down star formation in a process called quenching. This feedback mechanism helps explain why some massive galaxies stop forming stars and evolve into elliptical galaxies. Without this regulation, galaxies would grow too large and too bright, in conflict with observations. Black holes, through their activity, act as galactic thermostats, balancing growth and stasis in the cosmic ecosystem. Supermassive black holes also play a role in galaxy mergers. When two galaxies collide and merge, their central black holes sink to the center of the new system, eventually forming a binary pair. Over time, gravitational interactions with stars and gas cause the black holes to spiral inward, eventually merging into an even larger black hole. These cataclysmic events are predicted to produce gravitational waves, ripples in space-time first predicted by Einstein and detected for the first time in 2015 by the LIGO Observatory. Future instruments may detect the gravitational signature of merging supermassive black holes, opening a new window into galactic evolution. There are also intermediate mass black holes, thought to bridge the gap between stellar mass and supermassive types, though they remain elusive. Discovering and studying these black holes could offer clues to the origin of their larger cousins. Similarly, not all galaxies host black holes of equal size. Some dwarf galaxies contain surprisingly large central black holes, challenging existing models and hinting at a more complex formation history. The presence of a black hole also influences the structure of its surrounding region. The inner part of a galaxy, the bulge and nucleus, is shaped by the black hole's gravitational pull and energy output. In some galaxies, the interaction of black hole-driven winds and star formation leads to the creation of nuclear star clusters, dense and compact regions full of stars orbiting perilously close to the central void. Culturally and philosophically, black holes have captivated the human imagination as symbols of mystery, transformation, and the limits of knowledge. They defy ordinary logic, bending light and time, and challenging our understanding of physics. In science fiction and popular media, black holes often serve as gateways to other dimensions or tools of cosmic destruction. In reality, they are engines of creation and destruction, maintaining a delicate balance in the universe. The study of supermassive black holes is not just a chapter in galactic astronomy, it is a central theme. These compact objects, once dismissed as theoretical oddities, are now understood to be integral to the formation, structure, and evolution of galaxies. As observational tools improve, particularly with the Event Horizon Telescope and future space-based gravitational wave detectors, our understanding of these giants will deepen. Black holes are no longer the end of the story, they are a driving force within it. In the grand narrative of the cosmos, black holes stand at the intersection of matter and nothingness, motion and stillness, order and chaos. They represent the universe at its most extreme, and yet their presence is essential to the elegance and coherence of galactic evolution. Their story is inseparable from that of galaxies themselves. Beneath the luminous stars and swirling dust of galaxies lies something invisible but immensely influential: dark matter. Though we cannot see it directly, dark matter makes up the majority of matter in the universe and acts as the hidden framework on which galaxies are built. Its presence explains numerous puzzling observations in astrophysics, and without it, our understanding of galaxy formation and cosmic structure would fall apart. Dark matter is not merely a cosmic curiosity. It is the scaffolding upon which the visible universe hangs. The discovery of dark matter's existence began with observations that didn't match expectations. In the 1930s, Swiss astronomer Fritz Zwicky was studying the Coma cluster of galaxies and noticed that galaxies were moving too quickly to be held together by the visible matter alone. The gravitational pull of the stars and gas wasn't enough. Zwicky proposed that some invisible dark matter was providing the missing gravity. His ideas were largely ignored at the time, but decades later, further evidence began to pile up. In the 1970s, astronomer Vera Rubin studied the rotation curves of spiral galaxies. According to Newtonian physics, the stars farther from the galactic center should orbit more slowly, similar to how planets farther from the sun move slower. But Rubin found that the outer stars and galaxies moved just as quickly as those near the center. This flat rotation curve suggested that galaxies contained far more mass than could be accounted for by visible stars, gas, and dust. Something unseen was holding them together: dark matter. Today, we know that dark matter makes up about 85% of the total matter in the universe. It does not emit, absorb, or reflect light, which is why it's called dark. It interacts primarily through gravity, and possibly through weak nuclear forces, but not through electromagnetic or strong nuclear forces. This makes it extraordinarily difficult to detect directly, but its gravitational effects are unmistakable. One of the clearest demonstrations of dark matter's existence comes from gravitational lensing, when the light from a distant galaxy or quasar is bent around a massive foreground object, like a galaxy cluster. The amount of lensing depends on the total mass of the foreground object, including both visible and dark matter. In many cases, the lensing is far too strong to be explained by luminous matter alone, implying a vast halo of dark matter. These dark matter halos are enormous, often extending far beyond the visible edges of galaxies. They are thought to have formed early in the universe's history and acted as gravitational wells that collected baryonic, normal, matter, gas, dust, and eventually stars. Without dark matter, the gravitational pull of ordinary matter alone would have been too weak to form galaxies in the time available since the Big Bang. In essence, dark matter provided the seed beds where galaxies could grow. Simulations of galaxy formation and large-scale structure in the universe, such as the Millennium Simulation or Illustris TNG, show that dark matter forms a cosmic web, an intricate network of filaments and nodes where galaxies and clusters are concentrated. Between these structures lie vast cosmic voids, relatively empty regions. This web-like structure matches observations of galaxy distribution on large scales and is consistent with models involving cold dark matter, CDM, particles that move slowly compared to the speed of light and thus clump effectively. Despite its central role in cosmology, the true nature of dark matter remains elusive. It may consist of hypothetical particles such as WIMPs, weakly interacting massive particles, axions, or sterile neutrinos. Other possibilities include more exotic entities like primordial black holes or modifications to the laws of gravity. So far, numerous experiments have attempted to detect dark matter particles directly: deep underground detectors, high-energy particle colliders, and satellite observatories, but no definitive detection has yet occurred. This ongoing mystery challenges physicists and astronomers alike. While the standard model of particle physics has been incredibly successful in describing known particles and forces, it does not include a candidate for dark matter. The search for dark matter is, therefore, not just about understanding galaxies. It may lead to revolutionary changes in fundamental physics. Dark matter also affects the evolution of galaxies. Because it does not cool like gas, dark matter can form large, stable structures early in the universe. As ordinary matter falls into these structures, it undergoes cooling, collapses further, and forms stars. This interaction between dark matter and baryonic matter determines the size, shape, and composition of galaxies. In some cases, collisions between galaxies can separate dark matter from stars and gas, as observed in the famous Bullet Cluster, offering direct observational proof that dark matter behaves differently than ordinary matter during such events. Furthermore, dark matter may have an impact on galactic rotation stability and star formation rates. Galaxies embedded in massive dark matter halos tend to be more stable, with reduced susceptibility to tidal disruption. Some theories suggest that dark matter particles could decay or annihilate, releasing faint signals like gamma rays or neutrinos, which scientists continue to search for with specialized instruments. The study of dark matter has philosophical implications as well. Most of the universe is composed of something we cannot see, touch, or directly detect. Our cosmic picture is dominated by a ghostly presence that defies our senses, yet shapes the cosmos in profound ways. This humbling realization challenges our assumptions about knowledge and observation. It also serves as a reminder that what we perceive is only a fraction of what truly exists. The hidden structure provided by dark matter enables galaxies to form, cluster, and evolve in ways that would otherwise be impossible. Without it, the stars we see in the sky, the planets we live on, and perhaps even life itself, would not have had a stable environment in which to emerge. Dark matter is not an afterthought. It is a foundational component of the cosmos, woven into the very fabric of galactic architecture. In the coming decades, the mystery of dark matter may finally be solved, either through direct detection of its particles or through deeper insights into its gravitational behavior. Until then, it remains one of the most tantalizing enigmas in all of science, a shadowy substance that shapes galaxies and governs their fate, quietly but undeniably. Galaxies are not simply static collections of stars and gas floating through space. They are complex, evolving ecosystems, teeming with dynamic processes that mirror, in some ways, the biological cycles of living systems. They are vast arenas where matter is constantly recycled, transformed, and redistributed. Understanding galaxies as ecosystems opens the door to a more holistic view of the universe, one that sees structure, function, and change in constant interplay. Within each galaxy, stars are born, live out their lifespans, and die, returning their enriched material to fuel new generations. Just as in a forest or ocean on Earth, nutrients are cycled through organisms and the environment. At the heart of this concept is the stellar life cycle. Stars form in cold, dense regions of galaxies called molecular clouds. These clouds, often composed of hydrogen, helium, and trace elements, collapse under gravity to form protostars. If conditions are right, nuclear fusion ignites in the core, giving birth to a new star. Depending on its mass, the star may live for millions to billions of years. During this time, it fuses lighter elements into heavier ones, releasing light and heat, energy that eventually influences the surrounding galactic environment. When stars die, they don't simply vanish. Low-mass stars shed their outer layers and leave behind white dwarfs, while more massive stars explode in dramatic supernovae, dispersing elements like carbon, oxygen, silicon, and iron into space. These explosions not only enrich the interstellar medium with the raw materials needed for planets and life, but also trigger further star formation by compressing nearby gas clouds. In this way, the death of one star becomes the birth cry of others, a galactic feedback loop that keeps the ecosystem alive and evolving. Supernovae and stellar winds also help regulate the balance of gas in galaxies. Without such processes, gas might collapse into stars too quickly, exhausting the supply and halting future star formation. This self-regulating feedback ensures that galaxies evolve over billions of years instead of burning out rapidly. Moreover, these processes create galactic winds, streams of charged particles that can extend far beyond a galaxy's visible edge, carrying away gas and dust and influencing other galaxies in the cosmic neighborhood. Gas plays a central role in maintaining the galactic ecosystem. Hydrogen is the primary fuel for star formation, and its distribution and temperature determine how productive a galaxy can be. In spiral galaxies, gas is often concentrated in the arms, where gravitational density waves compress it into star-forming regions. In elliptical galaxies, most of the gas has already been used or expelled, which is why they have older stellar populations and less active star formation. The availability and movement of gas are crucial indicators of a galaxy's vitality. Dust, though often seen as an obstacle in telescopic images, is another key component. It helps cool gas clouds, enabling them to collapse more easily into stars. It also plays a role in chemistry, allowing complex molecules to form on its surfaces. These molecules include organic compounds that are considered precursors to life. Dust absorbs and re-emits radiation, shaping a galaxy's energy profile and influencing its observable characteristics in different wavelengths. Magnetic fields add another layer of complexity. Though relatively weak compared to gravitational or nuclear forces, they help guide charged particles, shape the motion of interstellar gas, and influence the formation of stars and cosmic structures. In combination with turbulence and radiation pressure, magnetic fields contribute to the dynamic interplay that defines a galaxy's internal structure. Galaxies also interact with one another, affecting their ecosystems in profound ways. When galaxies pass close or collide, tidal forces can trigger intense bursts of star formation, often referred to as starbursts. These events can exhaust a galaxy's gas quickly, but result in the formation of massive numbers of new stars in a short period. Mergers can transform the shapes and properties of galaxies, turning spirals into ellipticals, for example. These interactions are not destructive in the way we might imagine collisions on Earth. Instead, they are transformative, allowing new ecosystems to emerge from the ashes of the old. Some galaxies harbor supermassive black holes at their centers, which can dramatically influence their surroundings. When these black holes actively consume matter, they become quasars or active galactic nuclei, emitting enormous amounts of energy. This can heat up or blow away gas, shutting down star formation in the central regions of galaxies. This form of feedback is another regulating mechanism, preventing galaxies from growing uncontrollably and contributing to their long-term evolution. Importantly, galaxies are not isolated. They exist in groups, clusters, and massive superclusters, often connected by streams of gas and dark matter. Galaxies within clusters can be stripped of their gas by the hot plasma between them, a process known as ram pressure stripping. This environmental effect can quench star formation and alter the evolutionary path of a galaxy. Thus, the galactic ecosystem extends beyond a single galaxy to encompass intergalactic interactions as well. Even the voids between galaxies play a role. These seemingly empty regions are not truly empty. They contain diffuse gas, dark matter, and cosmic rays. They can act as reservoirs, feeding material back into galaxies through cosmic inflows. In this sense, the entire universe functions as a giant ecosystem, with galaxies as its organs, working together and influencing one another across vast distances and timescales. From a broader perspective, thinking of galaxies as ecosystems challenges us to rethink our place in the cosmos. Our own existence depends on the recycling of matter within galaxies. The atoms in our bodies were forged in the hearts of stars, distributed through supernovae, and incorporated into new star systems like our solar system. In this sense, we are participants in the galactic cycle, not mere observers. The dynamic life of a galaxy ultimately gives rise to planets, oceans, and perhaps even consciousness. As observational technology improves, astronomers are beginning to track these ecosystem processes in finer detail. Instruments like the James Webb Space Telescope and ALMA, Atacama Large Millimeter/Submillimeter Array, allows scientists to peer into the dusty nurseries of stars, observe feedback from black holes, and study the movement of gas across galactic scales. Understanding galaxies as ecosystems also opens new philosophical and psychological avenues. It invites comparisons to natural systems on Earth, encouraging an appreciation of complexity, interdependence, and the flow of energy and matter. It also reminds us that cosmic evolution and biological evolution are not separate but interwoven, governed by the same fundamental forces and principles. Galaxies, like forests and coral reefs, are places of birth, death, growth, and transformation. Ultimately, galaxies are not just distant objects in the sky. They are vibrant, evolving entities, shaped by and shaping the universe around them. Seeing them as ecosystems enriches our understanding and deepens our connection to the cosmos, suggesting that life and complexity are not anomalies, but natural outcomes of the universe's unfolding story. Galaxies, as immense and dynamic systems, are governed by cycles that unfold over millions to billions of years. These astronomical cycles are essential to the evolution of galaxies, influencing the birth and death of stars, the distribution of matter, and the very architecture of the cosmos. Far from being static collections of matter, galaxies are in constant motion, with processes repeating and transforming in rhythmic, almost organic ways. Understanding these cycles provides insight into the long-term behavior of galaxies and deepens our grasp of how the universe evolves over cosmic time. One of the most fundamental cycles within a galaxy is the stellar life cycle. Stars are not eternal. They have beginnings, lifespans, and ends. The process begins in vast, cold molecular clouds, which can stretch across hundreds of light years and contain enough material to form thousands of stars. Under the influence of gravity, regions within these clouds begin to collapse, forming dense cores that heat up and eventually ignite nuclear fusion, marking the birth of a new star. This phase is often accompanied by the formation of protoplanetary disks around young stars, setting the stage for planetary system development. Stars spend the majority of their lives in a stable phase called the main sequence, during which they fuse hydrogen into helium in their cores. The length of this phase depends on the star's mass. Low-mass stars like our Sun can remain stable for billions of years, while massive stars burn through their fuel in just a few million years. As hydrogen runs out, the star evolves. Low-mass stars swell into red giants, while high-mass stars expand into red supergiants and may go on to explode in spectacular supernovae. These stellar deaths are not mere endpoints. They are transformative events that play a vital role in the galactic ecosystem. Supernovae are among the most energetic phenomena in the universe, dispersing heavy elements into the surrounding interstellar medium. These elements, carbon, oxygen, nitrogen, and others, are the building blocks of planets and life. Even the atoms in the human body, from the calcium in our bones to the iron in our blood, were forged in ancient stars and distributed through these cosmic explosions. In a real sense, we are the product of stellar cycles. White dwarfs, neutron stars, and black holes are the remnants left behind by dying stars, and each has its role in the galactic rhythm. White dwarfs, the cores of medium-sized stars, slowly cool and fade over time. Neutron stars and black holes, formed from more massive progenitors, are dense, exotic objects that can influence their surroundings through gravity, magnetic fields, or bursts of high-energy radiation. When in binary systems, these remnants can draw matter from companion stars, creating X-ray binaries or even triggering additional supernova-like events. Another important cycle is the recycling of gas and dust. As stars die, they release material back into space. This enriched gas mixes with existing interstellar material, cooling and collecting in new molecular clouds. Over time, these clouds collapse again to form new stars, and the cycle continues. This process, sometimes called galactic chemical evolution, gradually changes the composition of a galaxy's stars and gas over time. Older generations of stars tend to have fewer heavy elements, while newer generations are more chemically enriched. This cycling of matter also shapes the observable features of galaxies. Star-forming regions light up with bright, blue stars that burn hot and fast. Older areas, where star formation has slowed or ceased, tend to be populated by redder, longer-lived stars. This creates color gradients and structures like spiral arms or central bulges, where different stages of the stellar life cycle are dominant. Galactic disks, where most star formation occurs, contrast with halos, which house ancient stars and remnants from the galaxy's past. In addition to stellar and material cycles, galaxies also experience larger-scale orbital cycles. Stars within a galaxy orbit the center, often influenced by the mass distribution of both visible and dark matter. In spiral galaxies, stars orbit in relatively flat disks, with the entire structure rotating over hundreds of millions of years. This rotation helps shape features like spiral arms, which are not fixed collections of stars, but rather density waves that move through the disk, triggering star formation as they go. Our own solar system is part of this vast movement. It orbits the center of the Milky Way at a speed of approximately 828,000 kilometers per hour, completing one full orbit roughly every 230 million years. This journey, known as a galactic year, means that Earth has revolved around the galaxy's center over 20 times since its formation. During this orbit, the solar system passes through different regions of the galaxy, which may influence the influx of cosmic rays or encounters with interstellar clouds. Another fascinating aspect of galactic cycles is the periodic interaction and merger with other galaxies. While these events might seem cataclysmic, they are part of the normal life cycle of galaxies. Collisions can trigger bursts of star formation, redistribute stars and gas, and even result in entirely new galactic structures. Over time, galaxies grow through such mergers, accumulating mass and evolving into new forms. The Milky Way, for instance, has absorbed numerous smaller galaxies throughout its history and is on course to merge with the Andromeda Galaxy in about 4.5 billion years. These collisions do not often involve direct star-to-star impacts, due to the vast distances between stars, but the gravitational forces involved can drastically alter the dynamics of both galaxies. Tidal forces stretch and distort galactic shapes, funnel gas into central regions, and even awaken dormant black holes. These interactions are part of a long-term cosmic dance that continually reshapes the structure and composition of the universe. Cycles within galaxies are not confined to matter alone. Energy also plays a crucial role. Radiation from stars, supernovae, and black holes affect surrounding gas, either by heating it and preventing further star formation or by compressing it and triggering new activity. Galactic winds, driven by supernovae or active galactic nuclei, can blow material out of galaxies entirely, affecting not only the parent galaxy, but also its neighbors. This constant interplay of energy input and feedback creates a balance that determines a galaxy's ability to grow and evolve. These internal and external cycles are all woven into the broader evolution of the universe. From the microscale of a collapsing gas cloud to the macroscale of galaxy mergers and cosmic expansion, galaxies are dynamic, ever-changing systems. Each cycle, though incredibly long by human standards, contributes to the grand tapestry of cosmic history. They illustrate a universe in motion, governed by patterns that echo across time and space. For us, understanding these cycles is more than an academic pursuit. It connects the fate of stars, galaxies, and even life itself into a continuous story of creation, destruction, and renewal. Every breath we take is enabled by the oxygen forged in ancient stars. Every atom in our bodies has participated in this timeless process. By studying astronomical cycles, we learn not only about galaxies, but also about our own origins and our place in the immense, ongoing rhythm of the cosmos. The Milky Way is not only our cosmic home, but also one of the most studied galaxies in the universe. Its evolution spans more than 13 billion years, during which it has transformed from a turbulent cloud of gas into a majestic spiral galaxy with hundreds of billions of stars. Understanding how the Milky Way came to be reveals not just the processes that shaped our galaxy, but also the mechanisms common to galactic evolution across the cosmos. This story is still unfolding, with each new observation and simulation adding details to a complex, beautiful history of birth, growth, and change. The earliest seeds of the Milky Way began forming shortly after the Big Bang. In the young universe, dark matter clumps acted as gravitational wells that pulled in gas, allowing the first stars to ignite within them. These early star systems were small and irregular, but over time they merged with one another, creating larger and more organized structures. Through this process of hierarchical assembly, the Milky Way's initial components began to coalesce. The first stars in our galaxy, known as population 3 stars, were massive and short-lived, quickly dying in supernovae that enriched the surrounding gas with heavier elements. These early generations of stars helped form what is now known as the galactic halo, a roughly spherical region surrounding the central part of the galaxy. The halo contains some of the oldest stars in the Milky Way, as well as globular clusters, which are tightly bound groups of stars that orbit the galaxy like satellites. The halo also contains a significant amount of dark matter, whose gravitational effects extend far beyond the visible disk and help hold the galaxy together. As more gas settled into the galaxy's gravitational potential, it formed a rotating disk. This process was driven by the conservation of angular momentum. As gas collapsed inward, it spun faster and flattened into a disc-like shape, much like a spinning pizza dough stretches into a circle. In this disk, stars began to form in great numbers, eventually giving rise to the structure we now see, a disk with spiral arms winding outward from a central bulge. The central bulge of the Milky Way is a dense, spheroidal region packed with older stars. It may have formed through early mergers or by the inward migration of gas that triggered intense star formation. At the very heart of the bulge lies a supermassive black hole, Sagittarius A*, with a mass about 4 million times that of the Sun. Though invisible directly, this black hole's presence is inferred from the rapid orbits of nearby stars and the emissions of high-energy radiation from its surroundings. It plays a key role in the dynamics of the inner galaxy, though it is relatively quiet compared to active galactic nuclei in other galaxies. The spiral arms of the Milky Way are sites of ongoing star formation, tracing out regions where gas is compressed by density waves that move through the disk. These arms are not fixed structures, but patterns of enhanced density that sweep around the galaxy, triggering the birth of new stars as they pass through gas clouds. Young, hot, blue stars light up the arms, while older, cooler stars populate the spaces between. Star formation is not uniform, but is influenced by factors such as gas density, magnetic fields, and feedback from supernovae. In addition to the main disk and halo, the Milky Way is surrounded by a population of satellite galaxies. These include the large and small Magellanic Clouds, 2 irregular galaxies visible from the southern hemisphere, and dozens of smaller dwarf galaxies. These satellites interact gravitationally with the Milky Way, sometimes donating stars and gas or being torn apart entirely. Evidence of past mergers can be found in the form of stellar streams, ribbons of stars stretched out across the sky, remnants of smaller galaxies that were cannibalized by the Milky Way over billions of years. This process of galactic cannibalism has played a major role in the Milky Way's growth. By consuming smaller galaxies, our galaxy has gained mass, new stars, and fresh supplies of gas. This process continues today. The Sagittarius dwarf spheroidal galaxy, for example, is currently being disrupted and absorbed by the Milky Way, its stars forming arcs and loops around the galactic core. These events are not rare or unusual. They are part of the normal evolutionary process of galaxies. One of the most significant events in the Milky Way's future is its predicted collision with the Andromeda Galaxy. Currently about 2.5 million light-years away, Andromeda is moving toward us at roughly 110 kilometers per second. In about 4.5 billion years, the two galaxies are expected to merge, forming a new, larger elliptical galaxy, sometimes dubbed Milkomeda. While the collision will dramatically reshape both galaxies, the vast distances between stars mean that few, if any, individual stars will actually collide. Instead, their mutual gravitational pull will distort their shapes, trigger intense starbursts, and eventually settle into a more stable configuration. Despite being such a dynamic and violent process, galactic mergers are relatively gentle on stars and planets. Our solar system is unlikely to be destroyed in the collision with Andromeda, though its position within the new galaxy may change. Some simulations suggest it could be flung farther from the galactic core, while others indicate it may settle into a new orbit. In any case, by the time the merger completes, the Sun will have long since exhausted its fuel and evolved into a white dwarf. Even today, the Milky Way remains a galaxy in motion. Its disk is not flat, but warped, likely due to interactions with nearby satellite galaxies or dark matter substructures. The disk also ripples and oscillates, perhaps as a result of past mergers. Gas continues to fall into the galaxy from the intergalactic medium, fueling star formation and extending the life of the disk. Meanwhile, older stars gradually migrate outward, and new stars are born in waves and clusters. Our understanding of the Milky Way is enhanced by projects like the Gaia mission, which is mapping the positions and motions of over 1 billion stars with unprecedented accuracy. These data allow astronomers to reconstruct the history of the galaxy, trace stellar populations, and even identify stars that originated in other galaxies. As technology improves, we will be able to study the Milky Way in greater detail, building a clearer picture of its past, present, and future. One fun and humbling fact is that our solar system is currently orbiting the center of the Milky Way at an average speed of about 828,000 kilometers per hour. Despite this incredible velocity, it takes about 230 million years to complete one full orbit. This means that the last time Earth was in its current position in the galaxy, dinosaurs roamed the planet. The concept of galactic years gives us a sense of just how vast and slow these cosmic processes really are, even when they involve tremendous speeds. In summary, the evolution of the Milky Way is a story of continuous change. From its chaotic beginnings in the early universe to its current elegant spiral form, the galaxy has grown through mergers, accreted gas, formed stars, and recycled matter. Its future will include dramatic transformations, including a major collision with Andromeda. Yet through it all, the fundamental processes of galactic evolution will continue. By studying our home galaxy, we gain a clearer sense of how galaxies live, grow, and interact across the universe, and ultimately, how we came to be. Galaxies have long transcended their astronomical identities, inspiring countless expressions in human art, myth, and culture. While the scientific understanding of galaxies is relatively recent, only developing robustly in the 20th century, the aesthetic and symbolic power of swirling celestial forms dates back millennia. Across civilizations and disciplines, galaxies have appeared not only as objects of study, but as profound metaphors, archetypes, and visual icons of beauty and mystery. In this way, the cosmos does not just surround us. It lives in our stories, symbols, and collective imagination. Before telescopes revealed galaxies as immense, independent star systems, many were perceived as cloudy, star-like patches in the night sky. The name galaxy itself originates from the Greek Galaxias kyklos, meaning milky circle, a reference to the Milky Way's diffuse glow. Ancient cultures devised rich stories to explain this streak of light across the sky. In Greek mythology, it was said to be the milk of the goddess Hera, spilled across the heavens. The Maya associated it with the world tree, a cosmic axis connecting the earth to the spirit world. In many indigenous American traditions, it served as a celestial river guiding the souls of the departed. These myths highlight an important truth. Even without scientific tools, people recognize the sky as something grand, ordered, and deeply meaningful. The concept of spirals, one of the dominant shapes of galaxies, emerged in early art, architecture, and mysticism. From prehistoric petroglyphs to the Fibonacci spirals in nautilus shells and sunflower seeds, humans have repeatedly seen and celebrated spirals in nature. The spiral became a sacred form, often representing growth, the unfolding of consciousness, or the journey between inner and outer worlds. Once astronomers like Edwin Hubble revealed that spiral nebulae were actually galaxies, this shape took on even deeper significance. In modern times, the image of the galaxy has become a staple of both scientific visualization and popular culture. The Hubble Space Telescope, launched in 1990, has brought stunning galactic imagery into public view. Spiral arms lit by newborn stars, elliptical galaxies glowing like ancient embers, and tangled galactic mergers captured in mid-collision have entered the global visual lexicon. These images blend the technical and the transcendent, inviting people to contemplate both the mechanics of the universe and its aesthetic grandeur. Artists, filmmakers, and writers have embraced galaxies as both setting and symbol. In science fiction, galaxies are often used to represent vast arenas of space and time, backdrops for interstellar travel, alien civilizations, and cosmic dramas. The very phrase, "a galaxy far, far away," has become shorthand for imaginative escapism. Galaxies provide not just scale, but mystery, evoking the infinite potential of life and mind beyond Earth. In visual arts, galaxies appear in a wide range of media, from oil paintings and digital art to sculptures and installations. Artists like Vija Selmans have recreated star fields with painstaking detail, capturing the feeling of immersion in space. Others take a more abstract approach, using galactic motifs to explore ideas of time, emergence, and the sublime. Contemporary artists often blur the line between scientific imagery and personal expression, creating works that resonate with both cosmic and human dimensions. Galaxies also hold symbolic weight in philosophy and psychology. Carl Jung, the founder of analytical psychology, noted the spiral as a symbol of individuation, a psychological journey toward the self. In this view, the spiral galaxy becomes an emblem of inner development and expansion. Similarly, Spiritual traditions often invoke galactic imagery to suggest transcendence, unity, or the infinite. The idea that the universe is alive or conscious, sometimes referred to as panpsychism or cosmic consciousness, often uses the galaxy as a metaphor for a mind larger than our own. The connection between galaxies and consciousness has even entered neuroscience and AI. When brain scans are compared to large-scale maps of galaxies, similarities in structure emerge. Networks of nodes connected by filaments, complex hierarchies, and self-organizing patterns. Though these analogies are not literal, they resonate with the idea that the universe may mirror the mind, and vice versa. This sense of fractal repetition, of patterns within patterns, reinforces the notion that galaxies are not just out there, but also in here, within our thoughts, dreams, and neural architecture. In literature, galaxies often serve as metaphors for the unknown. Writers from Isaac Asimov to Ursula K. Le Guin have used them to explore themes of expansion, isolation, and interconnectedness. A galaxy can be a frontier, a prison, a family, or a single point in a vast moral or metaphysical map. The sheer number of galaxies, estimated in the trillions, challenges authors and philosophers alike to consider humanity's scale and significance. What does it mean to be a conscious being in a universe with so many possible worlds? Cultural representations of galaxies continue to evolve as our technology and understanding improve. Virtual reality and planetarium projections allow people to experience galactic environments firsthand, zooming through stars and nebulae in immersive 3D. Educational programs use these tools to teach astronomy, while artists and designers use them to create new forms of cosmic storytelling. Galaxies thus become not just symbols of knowledge, but vessels for participatory wonder. Social media has also democratized access to galactic imagery. People around the world can now download, remix, and share NASA images, incorporating them into everything from fashion to music videos. This blending of scientific data and personal creativity creates a new kind of cultural space, where galaxies inspire not just awe but agency. They become platforms for imagination, tools for learning, and icons of a shared, planetary identity. Yet despite their prominence in modern culture, galaxies remain elusive in meaning. Are they merely physical systems, or do they carry deeper resonance? Is our fascination with them rooted in biology, evolution, or something more transcendent? These questions reflect the central tension of all cosmic art, the balance between knowledge and mystery. Galaxies can be measured, classified, and simulated, yet they still invoke feelings of wonder that defy easy explanation. In the end, galaxies in art and culture reflect our deepest longings to understand the universe, to find our place within it, and to express the inexpressible. They remind us that science and art are not separate realms, but intertwined ways of seeing. Through their forms, motions, and unimaginable scales, galaxies invite us to look outward and inward across the vast expanse of space, mind, and meaning. As scientific understanding advances, the concept of a singular universe, our universe, has been challenged by the provocative idea that it may be just one of many. This concept, known as the multiverse, expands the boundaries of cosmology, philosophy, and even metaphysics. In this context, galaxies are no longer simply the largest recognizable structures in space, but perhaps repeating or diverging phenomena in an unimaginably vast and varied ensemble of universes. What, then, becomes of galaxies when we step beyond the boundaries of the known cosmos and consider the multiverse? The multiverse theory arises from several branches of modern physics. One key source is cosmic inflation, a theory that suggests the universe underwent a rapid expansion in the first fraction of a second after the Big Bang. Some models of inflation propose that this process did not occur uniformly, but instead generated many bubble universes, each with its own physical laws. In this model, our universe is just one bubble among countless others in an infinite cosmic froth. Each bubble might have its own version of galaxies, or none at all, depending on the values of fundamental constants like gravity, electromagnetism, or the cosmological constant. Quantum mechanics offers another route to the multiverse through the many-worlds interpretation. In this framework, every quantum event with multiple possible outcomes results in a branching of reality into separate, non-interacting universes. If true, then countless versions of galaxies, perhaps subtly different in structure or history, exist in parallel. Some may contain slightly altered versions of the Milky Way. Others might hold radically different star systems or be devoid of galaxies entirely. String theory, a candidate for a theory of everything, also allows for a multiverse. Its mathematical frameworks suggest the possibility of a landscape of possible universes, each with different values for the fundamental parameters of nature. Among these, only a small fraction might be suitable for the formation of galaxies, stars, and life. This idea gives rise to the anthropic principle, the notion that we observe this particular universe with its life-supporting galaxies precisely because it allows for observers like us to exist. If galaxies can exist in other universes, what might they look like? Some speculative models imagine antimatter galaxies, vast systems built from particles with reverse charge. In such a universe, physics might still support structure formation, star cycles, and potentially even life, but all governed by a different chemistry. Other models imagine universes where the speed of light is different, or where gravity is far weaker or stronger, leading to galaxies that are far more diffuse, or collapse instantly under their own weight. Still more radical ideas include mirror universes with reverse time arrows or brane worlds, where galaxies form on different dimensional membranes within a higher dimensional space. These ideas remain deeply theoretical and far beyond the reach of current experiments, yet they provide a fertile ground for thought. If galaxies are one of the universe's basic motifs, then their echoes, or inversions, might be found throughout the multiverse. The concept of living galaxies has also emerged in speculative cosmology and science fiction. If galaxies are dynamic, self-regulating systems with complex internal interactions, ranging from feedback loops in star formation to the regulating effects of supermassive black holes, could they be considered, in some sense, alive? Some thinkers propose that sufficiently advanced civilizations might even transform entire galaxies, creating what are known as Kardashev-type 3 civilizations. In a multiverse, these galactic-scale entities might not be anomalies, but common outcomes in certain universes with favorable conditions. On the philosophical front, the idea of a multiverse raises profound questions about uniqueness and significance. If an infinite number of galaxies exist, does that diminish the value or meaning of our own? Or does it elevate the wonder, implying that nature endlessly experiments with form, law, and structure? Galaxies in the multiverse become more than objects of study. They become expressions of possibility itself. They challenge anthropocentrism and expand the canvas on which humanity paints its understanding of reality. From a psychological and existential standpoint, the multiverse forces us to re-examine our place in the cosmos. Just as Copernicus displaced Earth from the center of the universe, the multiverse displaces our universe from being unique. Galaxies in this framework are not just far away in space, but foreign in ontology. They may follow different rules, evolve differently, or even operate on principles beyond our comprehension. This decentering is both unsettling and liberating. It invites humility while also igniting the imagination. The question of whether these alternate galaxies can be observed or interacted with remains open. Some physicists argue that other universes may be forever inaccessible due to the speed of light and the structure of space-time. Others propose that quantum entanglement, gravitational waves, or exotic particles might someday provide evidence for other realities. There is even speculation that anomalies in the cosmic microwave background or the distribution of galaxies might hint at collisions between universes, a sort of cosmic bruising from impacts that occurred before inflation smoothed everything out. In literature and science fiction, the multiverse has become a popular setting for exploring identity, causality, and consequence. Galaxies are often used as symbols of choice, divergence, and alternate histories. Stories that span multiple universes frequently feature characters who travel between versions of their lives, discovering radically different outcomes in worlds that evolved from different cosmic seeds. Galaxies in these narratives function not only as locations, but as metaphors for the multiplicity of experience. Despite its speculative nature, the multiverse hypothesis underscores a core truth of modern science. The cosmos is far more diverse, dynamic, and strange than once imagined. The galaxies we see through telescopes may be only a thin slice of what is possible. Each one is a reminder not just of the richness of our universe, but of the infinite ways structure and beauty might manifest elsewhere. The very existence of galaxies in our universe, a delicate balance of forces, constants, and history, may itself be evidence for the multiverse, suggesting that among countless possibilities, ours was one in which galaxies could form and observers could ponder them. In the end, contemplating galaxies in the context of the multiverse invites us to dream in cosmic dimensions. It merges science, speculation, and philosophy into a single inquiry. What else could there be? And in imagining the vastness of those answers, we come to see galaxies not only as systems of matter and energy, but as portals to understanding the deep structure of all reality. Despite the incredible progress made in understanding galaxies, from their formation in the early universe to their evolution and structure, many fundamental questions remain unanswered. These mysteries are not merely gaps in data. They represent the frontier of modern astrophysics, the puzzles that continue to challenge our theories, inspire new technologies, and stir deep philosophical reflection. Each unresolved question about galaxies holds the potential to revolutionize our understanding of the cosmos. One of the most profound mysteries is the question of why galaxies spin so fast. Observations of spiral galaxies show that stars in their outer regions orbit the center at speeds that defy classical Newtonian predictions. According to visible mass alone, these stars should be flung out of the galaxy, yet they remain in orbit. This discrepancy led to the hypothesis of dark matter, a form of matter that does not emit, absorb, or reflect light, making it invisible to telescopes, but which exerts gravitational force. The existence of dark matter helps explain galactic rotation curves, gravitational lensing, and the large-scale structure of the universe. Still, after decades of searching, no direct detection of dark matter particles has been confirmed. What is dark matter made of? Is it a particle, a field, or something else entirely? Until we understand its true nature, our models of galaxies remain incomplete. Another persistent enigma is the question of what triggers galaxy formation in specific regions of the universe. While we understand the role of dark matter halos and primordial gas clouds in early galaxy formation, the exact mechanisms that determine where galaxies form and why some regions remain empty are not fully understood. The cosmic web, a vast network of filaments and voids, is visible in large-scale surveys. But the processes that sculpted this structure are still being modeled and debated. Why are some voids almost completely devoid of galaxies, while others are densely packed? What role do cosmic magnetic fields or exotic particles play in this distribution? Even more intriguing is the possibility that galaxies themselves may have life cycles analogous in some ways to living organisms. Galaxies are born. They grow through mergers and accretion, and they change shape and composition over time. But do they die? Some researchers propose that galaxies may reach a state of quenching, where star formation slows or halts entirely. This could be due to depletion of gas, heating from central black holes, or environmental effects in galaxy clusters. These dead or passive galaxies continue to exist but no longer produce new stars. Understanding how and why galaxies quench could illuminate the long-term fate of cosmic structures. Are there stages of galactic senescence or even rebirth? Another question that remains open is what lies within the vast voids between galaxy clusters. These regions, sometimes hundreds of millions of light years across, are among the most empty places in the universe. However, empty is a relative term. Some studies suggest that voids may still contain low-density gas, faint dwarf galaxies, or even exotic forms of matter or energy. Could they hold clues about dark energy, the mysterious force accelerating the universe's expansion? Are they simply statistical outcomes of gravitational evolution? Or do they point to deeper principles of cosmic balance and contrast? The relationship between galaxies and supermassive black holes is also an ongoing puzzle. Nearly every large galaxy harbors a massive black hole at its center, often millions or billions of times the mass of the Sun. Surprisingly, there appears to be a tight correlation between the mass of the central black hole and the properties of the surrounding galaxy, such as the velocity of stars in its bulge. But how can a relatively small region, a black hole's event horizon is minuscule compared to an entire galaxy, regulate or be regulated by the larger galactic structure? This black hole galaxy coevolution hints at feedback mechanisms that we do not yet fully understand. Do black holes control galaxy growth, or is it the other way around? Galactic magnetic fields are another area of mystery. Though weak compared to Earth's magnetic field, they extend across vast distances and influence gas motion, star formation, and cosmic ray propagation. How these fields arise, evolve, and affect galactic dynamics is still under investigation. Their role is often left out of large-scale simulations due to complexity, but they may prove to be a missing piece in understanding galactic ecosystems. We also face mysteries at the scale of galaxy clusters and superclusters. The largest structures in the universe are still forming today, merging through gravitational attraction. Observations of the Bullet Cluster, for instance, offer compelling evidence for dark matter, but also raise questions about the interactions of normal and dark matter during collisions. Meanwhile, some clusters appear to defy expectations by forming earlier or growing faster than models predict. Are there unknown physics at play? Could modifications to general relativity be required? Even the shape and distribution of galaxies raise questions. Some spiral galaxies have perfect symmetry, while others are lopsided or disturbed. Why do some galaxies develop bars, central linear structures crossing their bulges, while others do not? Why do certain galaxy types dominate in different environments, such as ellipticals in clusters and spirals in the field? These morphological variations are influenced by both intrinsic processes and cosmic environment, but the detailed interplay is still being studied. On the speculative side, scientists have pondered whether advanced civilizations could leave detectable imprints on galactic scales. Could a galaxy be reshaped by an intelligent species engineering stellar systems or manipulating black holes? This idea lies at the intersection of astrophysics and the search for extraterrestrial intelligence, sometimes called Dysonian SETI. Though entirely hypothetical, it opens new perspectives on what galaxies could contain beyond gas, stars, and dust. In the end, the study of galaxies is not just about cataloging stars or mapping shapes. It is a profound search for meaning in the universe's structure. Each unanswered question is a call for deeper inquiry. With upcoming observatories like the James Webb Space Telescope, the Vera C, Rubin Observatory, and next-generation gravitational wave detectors, the coming decades may transform many of today's mysteries into tomorrow's discoveries. But it's also likely that each answer will unveil new layers of complexity. The mysteries of galaxies are not limitations, but invitations. They remind us that we are at the frontier of human knowledge, peering into the depths of space and time with tools that grow more powerful every year. To study galaxies is to embrace the unknown, to follow the threads of gravity, light, and thought into a universe more intricate and beautiful than we can yet imagine.